Okay. So today we're going to continue talking about enzyme kinetics. We're going to kind of go back a little bit and think about the theory behind enzyme kinetics. We talked on Tuesday about the Michaelis-Menten equation and how that described an enzyme catalyzed reaction, and that was actually determined by, it was determined empirically, where they did experiments, got the data, and then said what type of an equation fits what we're seeing. We're going to kind of go back and think about it in terms of theory, what an equation like that should look like, and how that actually does, in fact, end up looking like what Michaelis and Menten described. So we'll talk some about the theory, move into practice. That is, once you have a protein, an enzyme, and you want to know some of these kinetic parameters that we have been and will continue to talk about, how it is that you actually measure it. And then we'll talk about reversible inhibition, two forms of it, and then allostery, which you should be kind of familiar with. Okay, so Briggs and Haldane, they took a theoretical approach. And the first thing that they had in their model is that if you have a substrate binding to an enzyme, that's going to form some enzyme substrate intermediate. Okay? And that formation of this, every time we see a small k, what does that refer to? A rate constant, and a large K is an equilibrium constant. So this enzyme and substrate, they're coming together, and there's some rate constant for the formation here. There's some rate constant for the dissociation there. And the production of product, right, is going to be the concentration of this intermediate times some rate constant, which they defined as K cat. So K cat is the actual rate constant for the catalytic step, for the breaking of bonds or the forming of bonds. All right? Okay, so what is it that we know? We know that whatever is going on here, what is going to define the velocity of the reaction with respect to the appearance of product? It's going to be this concentration times that rate constant, right? All right. So for the most part in the reaction, we have the enzyme there in small amounts relative to the substrate, right? It's catalytic. So we know a couple of other facts about these parameters. First, the substrate concentration is going to be in vast excess to the total amount of enzyme. And that total amount of enzyme, how is that being partitioned? We know that that total enzyme has got to be equal to the concentration of the free enzyme plus the concentration of the enzyme substrate intermediate. All right? So this is their model. These are things that we know for a fact. They then made an assumption in their theoretical model, and that is a steady state assumption. The steady state assumption is that you're going to get the formation of this, right? K cat, it's a rate what? A rate constant. So if this is a rate constant, and if this concentration is constant, then the velocity of the reaction is going to be constant, right? The rate of appearance of product will be linear as a function of time. So what does that look like? they're making this assumption that the change in the enzyme substrate intermediate over time is zero. So what's happening here is we'll call this pre-steady state at the outset of the reaction. Here's your concentration of substrate in orange. The concentration of the enzyme, which is the free enzyme, is in black. The concentration of the enzyme substrate intermediate is in red, and the concentration of the product is in blue as a function of time. So early on, the free substrate concentration is dropping. The free enzyme concentration is dropping because they are forming the enzyme substrate intermediate. Once they get to this point, the steady state assumption is saying this concentration is going to remain fairly constant for most of the reaction until the substrate concentration starts getting so low that then this comes down. All right? During that time, where the velocity of the reaction is constant, remember we talk about the velocity being a tangent, or when you plot the product concentration versus time, it's going to be a straight line. So during that time, that is when ES is constant. If ES is constant and the velocity is that times the kcat, then the velocity is constant. Okay? So what their model was when the enzyme and the substrate come together, they form this intermediate, and that intermediate concentration is going to be constant for most of the reaction. Okay. So here's their model. In the notes I gave you how you can do your gymnastics mathematically to get to this equation, right? But if you take this, you can show mathematically, and it's there in the notes for you, that we know that this velocity, okay, we said that the velocity for the reaction is what? It's kcat times the concentration of the enzyme substrate intermediate. What that ends up being is this, and that's the velocity is kcat. You don't have to worry about the derivation of this, obviously. What's going to be important here is that when you look at this equation and we look at Michaelis-Menten, you'll understand the similarity. So at this point, that equation is entirely derived from theory, from Briggs and Haldane. Michaelis-Menten, we went over on Tuesday, and that was empirically derived. So if you look at these two equations, all right, where are the similarities? We know, okay, that this is Michaelis-Menten. They described a Vmax. Briggs-Haldane in the numerator, they come to a term of kcat times E tot. Okay? What is the maximal velocity? The maximal velocity that can be achieved in this step would be kcat times ES, but the maximal that you could ever achieve would be if all of the enzyme was in the enzyme substrate intermediate. So this term, Vmax, does make sense with respect to that. In the numerator, you're multiplying that times the substrate concentration. That's the same. The denominator, you've got Km plus the concentration of substrate. You've got this term plus the concentration of substrate. So when you look at these two equations, right, you see that whether you derive it theoretically or experimentally, they end up looking very much the same. So now, what's the difference? We talked about Km as being what? In the Michaelis-Menten equation, yes, the concentration of substrate at which you have 1/2 maximal velocity. That was their empirically derived term as they saw from that curve. So now when you look at it, right, Km is equivalent to Haldane's term here. which is K minus the rate constants, K to the minus 1 plus K cat over K1. All right. So Michaelis-Menten says this term Km is equivalent to what Briggs-Haldane theoretically says is this. All right. So let's back up. This rate constant is, bless you here, enzyme and substrate coming together, forming this intermediate, or coming apart. Coming together, coming apart, coming together, coming apart, coming together, all right? This step is the catalytic step. Which step do you think would be the slowest? Something in terms of binding, dissociating, or a chemical transformation where you're having to break bonds, hydrolyze, make new bonds. K-cat is going to be slower, all right? And in fact, it is, and dramatically so relative to these two rate constants. So if it's the slow step, then K minus 1 or K1 are going to be much greater than K-cat. So what happens to this term? If this number is very large relative to that, then it essentially comes down to this, K minus 1 over K1. And what is that? That is equivalent to the equilibrium dissociation constant of that ES, right? So if you have ES and it's dissociating, right, because you've got K minus 1, which is the breakdown rate, over K1, which is the formation rate, that equilibrium dissociation constant is this. So the important point here is when you look experimentally versus theoretically, the equations converge. You have two interchangeable terms that when you look at it, you learn something else about Km. And what Km is, it's a measure of the dissociation of the ES intermediate. All right? So if Km is low, what does that tell you about the stability of the enzyme substrate intermediate? It's fairly stable, right? We're taking K-cat out of the equation, no pun intended, to simply focus on the dissociation, not the transformation, but the dissociation of ES. So Km, therefore, if it's a low dissociation, if Km is low, that means you have high affinity. If the Km is high, you have lower affinity. All right, so we've got that kind of inverse logic like we talked about with pKa's. The important point there is the Km term in all these equations. Km is telling you the binding affinity that an enzyme has for a substrate. All right? Okay. So now let's focus on K-cat a little bit. We know that K-cat times the total enzyme concentration, that would be the scenario that could give us the maximal velocity if all the enzyme is sequestered into that intermediate. What do we know about the terms of Vmax, the units? Molarity over time. So if you rearrange that, what you find is that the units for K-cat is per second. So that's going to be a number per second, and what that number refers to is the number of molecules of substrate that are being turned over into product per second per molecule of enzyme. All right? So we're talking now about the turnover number. So the Km term tells us something about what? Affinity. The K-cat tells us turnover, or the catalytic efficiency. So, if we look at Michaelis-Menten, here's the Michaelis-Menten equation. So what we're doing now is trying to appreciate what it is that the value of kcat over km tells us. All right? Let's say that we're going to do an experiment and we're going to set it up and we have our enzyme there and we put in substrate concentration. We put in substrate, but we put it in at a concentration that's not so high that it's just going to drive the reaction, but it's very, very low. All right? It's very low with respect to the Km. Why do we want to do that? At a very low concentration of substrate, when we then look at the velocity, that tells us how well does the enzyme and substrate come together and work together, right, when we've got very low amounts of it. It's really the best reflection of the inherent ability for the enzyme to find the substrate when the concentration is low and bind it, and then chemically transform it. So if we say at very low substrate concentrations, how well does this enzyme work? How well can it find, bind the substrate, and then chemically transform it? Those are the conditions where substrate concentration is very low. When the substrate concentration is very low, then this Michaelis-Menten converts to this. That is, this number here is very low relative to Km, so that denominator essentially is Km. Second point, we said that once you get to the steady state level, where's the enzyme? It's all hooked up in the enzyme substrate intermediate. But if you do this experiment and you say, we want to measure the initial velocity when the enzyme is added and the substrate concentration is very, very low, at that early time, most of that enzyme is free, right? Only a little bit has grabbed the substrate, and we want to look at that burst of formation of product. So when the substrate concentration is very, very low relative to the Km, most of the enzyme is still free. It hasn't reached steady state yet. So then we get this term from here. So when we look at that, and we talked about reaction orders, and we talked about velocities, first of all, what is the order of that reaction? It's second order. It's dependent on the concentration of the enzyme and the concentration of the substrate. This term in front of that must therefore be what? A rate constant. So this value, kcat over km, is essentially the same as a rate constant for the second order reaction between the enzyme and the substrate. All right? The theoretical maximum for that would be 10 to the 9 per mole per second. And what that would mean, right, when you do the theory, is that when it was under these conditions, very low substrate relative to the Km, that just by Brownian motion, just by random collision, once the enzyme and the substrate touched, the substrate was instantly transformed into product, right? So just by passive diffusion, when they touch, it converted to product. Numerically, that would be 10 to the 9th. Okay, you don't have to worry about that number. All right, so let's go back here. So kcat over km, what is that? It's acting as a rate constant for this second order reaction. So if things are going to go faster, right, if the velocity is going to be greater, then we would want the rate constant to be what? If you do an experiment and you've got a certain concentration of enzyme, certain concentration of substrate, if this number goes up and these are constant, then what must this term do? it has to go up, right? So for the velocity to go up in an enzyme catalyzed reaction, the value of Kcat over Km must be greater. You got, all right? You guys following this?
Yeah.
How do you make that term bigger? You can do it one of two ways. Increase the numerator or decrease the denominator. Now let's see if that makes sense. To increase the numerator, that means that the turnover number is higher. So that means the catalytic efficiency, once the enzyme has bound the substrate, it beats on it real quickly and converts it to product. Okay? Question? In this, we're just saying if we want to take a snapshot in time, and we want to say when things are very minimal, right, when we put it and look in a reaction at a condition where the enzyme has to find the substrate, bind it tightly enough to get it in its grasp, and then do something to it, right? This is the equation that we would use. Let's take the extreme example. The extreme example is we dump a ton of substrate in there, and it overwhelms the enzyme. Would that tell us anything really about the affinity that the enzyme has for the substrate? It's being overwhelmed. So if you put them under rather Spartan conditions and you say, all right, times are tough, let's see how good you can get it done now, then that's the best reflection. So if an enzyme is designed to act on a certain substrate, what things must be taken into consideration? The first thing it has to do is, right, the enzyme has to bind the substrate and hold on to it. The next thing it has to do is chemically transform it. So both of those things come into play. When I lived in Boston as a postdoc, we had a female cat. She was an indoor cat, and we had a bird feeder outside. And one day, she got out of the house, and she was sitting under the bird feeder, not moving. And we went outside and looked, and she was just sitting there with a stupid look on her face, and there was a feather in her mouth. And my wife at the time grabbed her mouth, opened it, and a bird flew out. Alive.
Oh my God.
Okay? So even though it's a true story, even though it is cat versus Kcat, it demonstrates something. If an enzyme has a very low Km, it can bind something really well and hold on to it, and then it sits there and does not know what to do with it, right? And it does not chemically transform it. Is that a good strategy for that enzyme? On the other hand, you've got a smart cat that once it gets a hold of something, it's going to chemically transform it instantly. But this cat is so fat, it is so slow, it doesn't have the affinity. It says, I've got a high Kcat. If I bind it, I'm going to chemically transform it. But if it can't find it and can't bind it, is that a good strategy? No. So the important point in all of that is that when you look at that term, Kcat over Km, that really is a very good indicator of the overall efficiency of an enzyme, because it takes into account both things that it has to do. It has to find and bind its substrate with a reasonable affinity, and then it has to chemically transform it. If it's a super binder and a poor catalytic converter, that's not good. Vice versa, you got to strike a compromise. So when you look at these enzymes here, these are all hydrolases. You're getting hydrolysis. Don't have to memorize them, but from top to bottom, if we look at Kcat, that value is or Kcat over Km is 93, 1.7 times whatever, and this number is getting bigger and bigger. So as we go from this value of Kcat over Km to this, the enzymes are becoming more or less efficient. More efficient. So here, Kcat over Km can say, in theory, these are different enzymes. They're doing different things to different substrates, but if I want to be judgmental and stand back and say, all right, who gets the A, who gets the B minus, who's dog meat? Of all these, the most dog meat of them all is what? Chymotrypsin. So you look at it, its Kcat is what? 0.14. So about, if chymotrypsin has its substrate, that one molecule of chymotrypsin has its substrate, it'll turn that over, right, in about how much time? In about 7 seconds, right? You get 0.14 per second, so to get one molecule turned over, it's going to take 7 seconds, all right? You look at the Km, that number, 1.5 by 10 to the minus 2, is that a larger or a smaller number than, let's say, 9 by 10 to the minus 4? A larger Km is a what affinity? A lower affinity, right? So this guy doesn't have a very tight affinity for substrate, and once it gets it, it just sits there and takes its sweet time. So overall, not a terribly efficient enzyme, as opposed to fumarase, 5 by 10 to the minus 6. That's a very low number. That number is the blank constant of the ES intermediate. What's blank? Dissociation. Dissociation. So if 5 times 10 to the minus 6 is the dissociation constant, that tells you it's not dissociating that much. That means that once ES forms, right, that you're not going to dissociate. It's got a tight affinity. That's good. And now you look at the chemical transformation step, and it's 800 per second. So this thing does both things well. So Kcat over Km, in comparing one enzyme to another on different substrates, can tell you this is a pretty good enzyme, and it's overall more or less efficient than somebody else. Okay, so now let's say you have a given enzyme. All right, so here is chymotrypsin, and in most cases, you have an enzyme, and we'll look at the architecture of the active site and how this stuff works. But in the cell, an enzyme is going to work on something. But are there other things in the cell that typically look like that something? Yes. All right, so enzymes can work on related substrates. So then the question is, if you have related substrates and you present it to the enzyme, how do you determine what the best substrate is? What is the preferred substrate? How much specificity does that enzyme have to distinguish these substrates from one another? If someone says, well, you go ahead and you determine the Km, which we'll get to in a second, is that a suitable thing to do? It is partly, okay, because it's saying how well does it bind. But it doesn't tell you anything about once it has it, does it chomp down or just sit there stupid-like. The same thing for Kcat. So if you have a given enzyme and you want to determine what is the preferred substrate for this enzyme, you would go ahead and do the experiment. What is the experiment? We have a certain amount of enzyme in, and then we vary, right, the substrate concentration versus time, get the curves, and then I'll show you what we do with it, but we can get both Kcat and Km. You then say, what is Kcat over Km, and you have these. So of these numbers, which is the best or most preferred substrate? Phenylalanine, all right? And we're actually going to look at chymotrypsin and see why that's the case, all right? So when you're talking about overall efficiency or you're talking about preferred substrate / specificity, this is the term that you want to get. So how is it that we get that curve? What we do is what's called the Lineweaver-Burke analysis, or also a double reciprocal plot. Just so you know how this is derived. I was actually doing this last night in the middle of the thunderstorm, praying that we weren't going to lose power or I was going to come here this morning up to this point. What equation is that? Huh? MM. So we use MM for LB. If we take the reciprocal of both sides, we're just flipping them on their heads, right? So now 1 over velocity is Km plus S over Vmax times S, right? This term can be broken up, right? Km over Vmax times S plus S over Vmax times S, right? 1 over velocity, additional velocity here is now going to be Km over Vmax times 1 over S plus the substrate concentrations there cancel, and we get 1 over Vmax. All right? So this has the form y equals mx plus b, right? Where you are plotting y versus x, and m is telling you what? The slope of the line. So in the Lineweaver-Burke plot, we get the data, and rather than plotting it velocity versus substrate, we're looking at 1 over velocity versus 1 over substrate. If we plotted it velocity versus substrate, what type of curve would we get for a typical enzyme catalyzed reaction with no cooperativity? We get the rectangular hyperbola, right? But in the double reciprocal plot, we get a straight line. When you get the straight line, first of all, you know from this, Km over Vmax is the slope, all right? But when you project this line down to the x-intercept, right? When the at the x-intercept, what is the value of y? 0. So if this term is 0, then this term has to be equivalent to that term, but in the opposite sign, so that these two add to be 0. Suffice it to say that the x-intercept is minus 1 over the Km. All right? The y-intercept, the value for x is 0. What are we plotting on the x-axis? So if this term is 0, this term is, so 1 over velocity equals 1 over Vmax. So the y-intercept now is 1 over Vmax. And then we can see that the slope is Km over Vmax, but we can get both of those terms from the intercepts. If we know what Vmax is, and we did this experiment, we know how much enzyme went in, so we know what the total enzyme is. So what will we also know from determining the Vmax? The maximal velocity that we can achieve is Kcat times the total enzyme concentration. If the total, if all the enzyme was in that intermediate, the velocity would be equal to Vmax. So from the Lineweaver-Burke, we can get Vmax and Km. Since we know what enzyme concentration is, we know from the Vmax term what Kcat is, so now we know Kcat and Km, and we can determine efficiencies and specificities. Okay? Pretty clear? All right. So let's move to thinking about the reactions in some other ways, variables affecting the velocity. First of all, what we've been talking about is all of this being done at a certain enzyme concentration, right? You change the enzyme concentration, you're going to change your Vmax, okay? The substrate concentration relative to Km, temperature, and pH. So let's take a look at temperature first of all. Are we talking about chemical catalysis here or enzyme-mediated catalysis? It's enzyme-mediated. So in a typical reaction that's either uncatalyzed or it's chemically catalyzed, all right, as you increase the temperature, you're going to increase the velocity of the reaction. When you do that for an enzyme-catalyzed reaction, you start to see the same thing, and then you reach a temperature, and it goes down very quickly. Why? Because you've denatured the protein, all right? When you look at pH, this is a pH rate profile, and we'll get involved, we will look at this in greater detail. pH rate profiles are very important, and they're kind of classic manifestations of enzyme-catalyzed reactions. Why? When you change the pH from everything we've learned so far, or maybe whatever, we've got enzymes, proteins, side chains. Maybe they can ionize, maybe they can't. As we change the pH, we are changing charge, positives, minuses, neutrals, going back and forth. Very early on, I told you that these charges play important roles in both molecular recognition in terms of binding things, stabilizing interactions with substrates, and then the chemical transformation, and we'll look in detail. So we'll look in greater detail later, but when a curve goes like this, it says that as the pH goes up, something's getting better. But then, as you continue, it gets worse. So most proteins, do they have all positive charges or all negative charges? No. They're both. And so if you go to a very high pH, right, things are going to be very, very negative. And if you need positives for interaction or catalysis, you're out of luck. If you then go the other way, then I'm much more positive. And that may be great for some of the side chains that need that positive charge, and they can do what they can do, but there are other ones, right, which are protonated that shouldn't be protonated because they can't do what they have to do. So this pH rate profile, this is telling you the pH at which you've got the best compromise between your positive charges and negative charges that are involved in the reaction, right? And that's where you get the maximal velocity, but we'll look more in detail about that later. Okay. So reversible enzyme inhibition. An inhibitor is any compound that can decrease the rate of an enzyme-catalyzed reaction. Now we have reversible enzyme inhibition and irreversible. We're going to talk about reversible, and then I'll just mention something about irreversible. If it's reversible inhibitors, what that means is the inhibitor can bind to the enzyme and then come off, right? So it doesn't get locked on, and so it's going to have an equilibrium constant for this as well. Sorry about that. So the enzyme plus the intermediate is forming the enzyme plus the inhibitor is forming an enzyme inhibitor intermediate. All right. So the first type of reversible inhibition is competitive inhibition. So competitive inhibition is where the substrate and the inhibitor look kind of the same, and they're both going to the active site, right? So here's the active site. This is where the binding and the catalysis is taking place. So the substrate and inhibitor both go there, and they are competing, right, for the active site. So if the inhibitor's there, the substrate can't bind, and so that proper substrate, which is to give you the product that you want, that can't happen. So if we want to know whether an inhibitor is competitive or not, we have to do an experiment and then look at these kinetic parameters. You can go ahead and you can plot this, but you could also think about it. Don't even look here. And just look at it, just think about it. Don't look. If it's a competitive inhibitor and it's competing with the substrate, if you raise the substrate concentration, can you outcompete the inhibitor? Yes. So if you got inhibitor in there, it's slowing the reaction down. If you then just put a ton more substrate and it basically pushes it out of the way, is that going to change Vmax? No. The concentration of substrate that you need to get to Vmax is going to be higher, but it's not going to change Vmax. You can still get to that same velocity. So when you look at velocity versus substrate concentration, in the presence or absence of an inhibitor, in the presence or absence, you're still, now you can look, you're going to have the same Vmax. What will change? What will change is the Km, and the Km is going to be an apparent Km, and it's going to increase. Why? This is your Km minus inhibitor. This is the Km plus. Because when the inhibitor is there, where is the inhibitor going? To the active site. So it is competing with the substrate for the active site. So let's say you didn't know. Let's say you were doing reactions in your lab and the person across the bench from you doesn't like you very much and they want to make your life more complicated. So in one of your buffers that you use, they throw in an inhibitor. It's a competitive inhibitor. You go ahead and you do this and you go, Jesus, look at this Km. This Km is really high. This protein doesn't like to bind, right? The enzyme doesn't like to bind this substrate very well. What's really going on is the inhibitor is there and it's binding to the active site, precluding or excluding the substrate. So it gives you the appearance that the binding is poor. So you can ultimately drive it off with higher substrate concentrations, but we define Km as being the substrate concentration at which you have half maximal velocity. So competitive inhibition, the kinetic manifestations of that, whether you do it by a standard Michaelis-Menten plot or a Line-Weaver-Burke, the Vmax does not change. You can always get to that high velocity. It just looks like your binding, okay, is weaker, and it is because there's somebody else in there mucking up the works. Non-competitive inhibition. Non-competitive is where the inhibitor is binding some other part of the enzyme molecule. So whether the substrate is there or not, right, the inhibitor site is over here, the active site is here. So substrate can, inhibitor can bind here, whether substrate is there or not, but when that inhibitor binds, okay, it decreases or eliminates the activity of the enzyme. So, in that situation, what is going to happen if you increase the substrate concentration to try to drive that inhibitor off? It's not going to do anything. So it is non-competitive. So when you look for non-competitive, right, because you're not getting competition at the active site, the affinity or the apparent affinity that the enzyme has for the substrate is unaffected. So Km is not changed, but Vmax is. And you can see that by either that curve or Line-Weaver-Burke. So this is important. I mean, this is basic enzymology here in terms of determining these parameters. So you have to be able to interpret what that curve looks like, what it tells you, or if you see it in that form, what it tells you. And why is it that we would like to do this? Either in terms of testing molecules for their potential inhibitory actions on enzymes to do productive things, we need to know what types of mechanisms are going on. Is something competitive? Is it non-competitive? Okay, I'll tell you one other type. So here Non-competitive and competitive inhibitions are two flavors of what type of general inhibition? Reversible. Okay? Why is it reversible? It's reversible because, remember, the enzyme binds the inhibitor, but they can come off of each other. Okay? In other words, in this case here, if you put inhibitor in, and as soon as it bound to the enzyme, it killed it, you would never get up here, right? So by definition, reversible inhibition, the inhibitor binds to the enzyme in a reversible fashion, all right? Irreversible inhibition is different in that as soon as the enzyme binds that inhibitor, somehow it becomes a suicide mission, all right? And usually what happens, let's say you had an irreversible inhibitor. Would you think most likely that that would bind in the active site or somewhere other than the active site? It would be the active site, because if it's somewhere else, what kinds of interactions are usually occurring there? Hydrogen bonds, salt bridges, etc. And those usually are going to be in equilibrium. Where irreversible inhibitors reside are in the active site, and they will go in there and they will look like the substrate, but they'll be altered in some way so that the enzyme says, I've got my substrate, I'm going to do the chemistry on it because I recognize this portion as being important for breaking bonds, forming bonds, whatever. It'll start to do that, but then the rest of the molecule is not conducive to finishing the reaction and throwing it out. Remember we said enzymes catalyze, they start to catalyze a reaction, and then they have to come back to where they were before so they can do it again. If the enzyme, if you give it a tainted pill and it starts to work on it in the active site and it makes a bond and now it goes to break a bond another way to release the product, and the structure is different, then it gets stuck, right? It started to act on it, can't do it, can't finish it, can't spit it out, so it's dead. So that's irreversible. Okay, real quick, allosteric control of enzymes. So this curve here is what we saw for hemoglobin. So hemoglobin was one example of homoallostery where the binding of one molecule, what did I say? Oh, well, it's one example of binding a molecule. For hemoglobin, it was oxygen, right? But it can be other things, and it can also be not necessarily just binding. So for example, here, let's say you have some substrate, and in the cell you really want to kind of keep it in that concentration range. So there are things that are making it, and then maybe this enzyme here would break this back down. You can have where once it reaches this concentration, it starts to stimulate the enzyme that's going to break it down. So that would be one in the active site, but maybe another one binding somewhere else. Why? If that curve is sigmoidal and there's some type of allostery, we know what? We have to get more than one molecule bound, right? And they don't have to be in identical binding sites. You could have one going in the substrate, one of the substrates going in the active site and another one going somewhere else because the concentration is so high, and when it's over on the other portion, it makes the enzyme work better so that it'll have a higher activity and drop this concentration down because we want to keep it in this range. That be an easier way to look at it, and what is more often seen is heteroallostery. So we talked about a couple of cases there for hemoglobin, but a simple thing would be in the cell, let's say you have an enzyme that's at the beginning of a pathway, and at the end of the pathway you have a product. When you have enough of that product, you normally want to say, I've had enough. Where are you going to go to shut things down? By feedback inhibition, you're going to go back typically to the beginning of that pathway. So a lot of times what you will see is the enzyme activity in that first step will be affected by the amount of the product. And if the product is high, right, that product is going to feed back and inhibit the enzyme of the first step that normally has a different substrate, so that is a form of heteroallostery, and that negative feedback would be a situation where you add the inhibitor and you're stabilizing the weaker form of the enzyme for the substrate either binding or acting on it, okay? So, what lectures today? 9? Okay, so we have 10, 11, and 12 that are going to be dealing with looking at the mechanisms of how all this stuff comes about.